All right. Today we're gonna continue talking about wave, obviously, and we're gonna wrap up the mathematics of wave a little bit with wave equation, and then we're gonna start talking about specifically sound wave, which is pretty important because that's something you encounter every day, right? So sound wave. So let's start first with wave equation. So this is kind of like also a review from last time because last time we introduced how we describe wave and not just any wave, right? The sinusoidal wave, right? So for example, what I'm trying to do is I'm trying to describe a wave, for example, on a string, and then I set up a coordinate like this. So vertical, I call it y in meter usually, and that's the displacement of the string from the equilibrium point. And then x horizontal is the location on the string. Okay, so the difference from a wave between wave and the simple harmonic motion that we talked about last week is that horizontally, if you have only one particle, the horizontal axis usually just time. But since we have like many particles on wave or on the string, which eventually gonna have some wave on it, um, you use the horizontal axis to specify the location of the point or the section on the string that you're interested in. So it looks like this. But you have to also remember that the shape gonna change with time. Okay. So for example, you might have the wave that looks something like this. Okay, at one snapshot of time, and then later on, this wave might be going to the right, something like this. Okay. So times passes, then the wave gonna also change. So we have um, a wave which is described by this function. So y depends on two free variables, which is the location on the string and time. So y is the function of x and t, right? So it's a multivariable function for y. And last time we showed that we can describe this, let's say, with sine function, but again, it can be cosine or it can be sine of something plus, you know, the initial position or the initial phase. But to simplify our mathematics, we're gonna assume that it's just described by a, which is the amplitude, right? So a is the amplitude. That's the maximum displacement any section on the string gonna have, right? So on the negative side, it's gonna be minus a. Okay, so a is the amplitude, and then sine of k x minus omega times time, like this. Okay, so I labeled this in blue because those two are the two free variables that you need to choose, and then you can get the value for the displacement this way. Okay, so we have two variables, which is x and t. So what we can do if we want to find the velocity, right? Velocity is the change of the displacement with respect to time, right? So you differentiate with respect to this variable t. So we have a v, and then I can add subscript y just to make sure that we are talking about the velocity of the section of the string. So let's say you put some mark on the string in red here, and then you watch this dot going up and down, right? That's what we showed last time. So the dot itself is not moving with the wave, but it's only moving up and down in this case. And because it's moving up and down as a simple harmonic motion, so we can calculate the velocity of this dot, which you should suspect that it's probably going to be something like sine or cosine also, right? But we showed this kind of explicitly last time by just a direct differentiation. So it's d by d of the variable t, right? Of the displacement, which is what we have in the previous line, like this. Okay, and because we have two free variables, when you write down the differentiation, you have to use this partial derivative. But for our purpose, you can just treat this as a normal derivative that you have learned in single variable calculus. So anything but t you can just treat as constant. So for example, in this case, x is a constant, right? Because that's not the variable that we are differentiating with respect to. Okay, so that makes it actually not that complicated to calculate the time derivative because it just works like normally. So you're gonna have minus a omega cosine k x minus omega t, like this. Okay, minus sign because of the minus sign in front of omega t here, and omega because of the omega in front of t here, right? So you apply like the chain rule once, and this is what you get. All right, and then next, what we did last time is we didn't stop here, right? We do another differentiation, which is the acceleration. So ay, which is a function of x and t, is also d by dt of the velocity, which also depends on two free variables. Okay, so you do the same thing again. So now you're gonna have minus a omega square, but then cosine becomes sine of k x minus omega and then t, right? And what we have done is nothing but to show you that the motion of any point on the string is simple harmonic. Why? Because if you substitute y equal to a sine into that equation, you get something like this. Okay, and that's something we have seen before. Remember when we talk about simple harmonic motion, right? What is simple harmonic motion is the motion in which the acceleration is directly proportional to the displacement with the minus sign. Okay, so we have the same thing here, and that's true for any x. Okay, what does that mean? It means that any x is any location on the string, right? You pick x, then you're gonna have this equation for that particular x, which is simple harmonic. So every point on the string behave like a simple harmonic motion oscillator going up and down. Okay, so this shows the connection between sinusoidal wave, where we are discussing now, to simple harmonic motion, which we talked about last week. Okay, so it's kind of very, very similar, except for wave you just have more than one oscillators. You have a lot of them joined together, like in this case. Okay, so this is kind of like what we did last time. Today we're gonna do a little bit more differentiation. So, but it's not gonna be any more different than what we did last time, except now we're gonna calculate the derivative of y with respect to, instead of t, now we do it in with respect to x, the location. Okay, we didn't really have like a name for this one. It's not like it's a velocity because it's not divided by time. So well, having no name is fine. Just call it dy by dx, right? So it's the same thing as what you did earlier, except now you do it with respect to x. So just to make it clear, I'm gonna copy down this line first so that you can see what I'm getting at, right? So it's the partial derivative with respect to x. So anything other than x you can treat as constant. So time is constant in this line here. So when you do the time derivative, you're gonna have something that looks like this. So a, right, amplitude stay the same, sine becomes cosine, right? And then d by dx, you are multiplying x by k, right? So k is a constant. So you have k in front also. So let me write it here. So k, okay? And then cosine kx minus omega t. Okay, so that's the first derivative of y with respect to x. So you can think of this as like a slope, right? Because you have like y and x, and then dy by dx, you know from calculus that it's just the slope of the line going through that particular point, right? So that's the slope. So this one gives you the slope, right? But we are not going to stop here. We're going to do another derivative. So we're going to do the second derivative, which is nothing more than just applying d by dx another time to the same function. Okay, so d by dx of this one more time. Okay, and well, it's simple enough so that I'm not gonna write out every, you know, small steps, but please convince yourself that this is what you're gonna get in the end. AK square sine kx minus omega t, right? So that's what we have here. Okay, and then you see something kind of familiar again, because a times sine kx minus omega t, that's y. Okay, so here you got minus k squared times y of x and t. All right, so what's the point of doing all of this? I can divide minus k squared both sides and then get minus 1 over k squared d by dx, well, second derivative of y as a function of x and t equal to y as a function of x and t. Right. So I have this equation. I also have another equation, which is this one. Okay. So what is this? This one, well, a acceleration in the y direction. If we write it down fully in terms of, you know, the second time derivative is d by dt, well, second derivative, right, of y xt equal to minus omega squared times y of x and t. So if I do kind of the same thing, I divide everything by 1 over omega squared with the minus sign, I get something like this, equal to y x and t. Okay, so this is the other equation, which is the same that with what we have up here, except, you know, written in a slightly different way. But these two equations, you can see that the right hand side are the same, which is just y as a function of x and t, right, on both sides like this. I have some drop connection. So can everyone hear me now? Did something froze? Well, I mean, I think my connection was down a few seconds. But is it better now? Can anyone hear me now? Okay, so now it's good. Okay, good. So I will continue then. And you can see the screen still, right? Okay, good. So we compare these two equations, which has the same right hand side, which is just y as a function of x and t. So I can equate them, right? So what I have is 1 over minus 1 over k squared d by dx y of x and t, right, equal to y of x and t, but which is equal to this one. So I can write 1 over omega square d by dt square, second time derivative of y, x and t like this. Okay, and then tidying this equation a little bit with the minus sign cancel out. So I have this. Okay, so I'm not going to write y as a function of x and t again because that's kind of many times. It should be clear by now that y is a function of x and t. And then k over omega square d by dt square of y, like this. All right. So what do we have here? Well, this, even though we use like y, which is a function of x and t in terms of sinusoidal wave, which is either sine or cosine. Okay, but in general, this is kind of, this applies to any kind of wave, not just sine wave or cosine wave. So this is what we call the wave equation. It's quite important, but unfortunately, or fortunately for you all, that we're not going to use this much in this class because it's, by the look at it, it's actually a partial differential equations, which in general is very hard to solve. Okay, but it's it's there, so you should at least be able to identify, okay, this is wave equation. So we call this a wave equation. So that means any function of x and t that we call y, any y of x and t that satisfies this equation is a valid wave. Okay, which is good mathematically, because if you want to see if any particular function is a wave or not, then you plug into this wave equation, and then you just see whether that solves this equation or not. If it does solve it, then it's a wave. If it doesn't, then it's not a wave, right? And we can do a little bit more, dissecting this, because it's not quite familiar to you, especially this term, right? K over omega. So let's take a look at k over omega a little bit. So what is k over omega, right? Well, what is k? If you remember, k is something to do with the wavelength, which is something that we call wave number. So by definition, it's 2 pi over lambda, which is the wavelength, and then divide by omega, which is 2 pi times f. Okay, this is just copying the definition that we had way back. All right, so 2 pi and 2 pi cancel out. So you have 1 over f times lambda. And this should ring some bell, right? Because f times omega, f times lambda, that's just the velocity of the wave, so 1 over v. Okay, so k over omega is just 1 over the velocity. And what velocity are we talking about? Is the velocity of the wave. So it's how fast wave is moving, right? So essentially the other form of wave equation, which is probably more familiar, is the second derivative of y with respect to x is just k over omega square, right? This is the same thing. I'm just copying. But now k over omega is 1 over v. So it's just 1, so I don't need parentheses. So 1 over v square d square y by dt square, right? So just looking at the wave equation, comparing this to any function that you want to try to solve it, then you can read off the velocity of the wave right away, which is anything that appear in front of d square y by dt square. That's going to give you the velocity of the wave. Okay, so in other words, the wave equation, which is this line, gives you, a mathematical tool to test whether your thing, the function that you have, is a wave or not. And actually, for those of you who are a little bit, like more mathematical oriented, then you want to actually show that. Remember from the beginning of our discussion of wave, we say that any wave is anything that has this form, x minus vt. Okay, so any function that has this form is a wave. For example, right, e to the minus x minus vt square, or even x minus vt square, which is a really strange wave, but mathematically it's fine. So anything that you can write in this form actually gonna solve the wave equation, right? So we are stating actually the same thing, one maybe a little bit more rigorously, like anything that satisfies this one, the wave equation is a wave, and it turned out to be like anything that has this form actually automatically satisfy this wave equation. Okay, so it's kind of like saying the same thing, but a little bit differently. Okay, so that's kind of the mathematics of wave. And again, we are not gonna spend too much time, like solving wave equation, because again, it's not really our main focus here. But one thing I want to mention, and you probably need to know the formula a little bit, is that you can show that if you have, a string, which is what we discussed from the beginning, right? And then you're trying to put some wave into this string, right? So wave in a string, right? And one question we might have is, what is the velocity of the wave in the string, right? So what property of the string, affect the velocity of wave? And it turned out that it depends on two things. So first, how heavy the string is. So we have the value which is called mu. This is the linear mass density. Which is essentially just the mass per unit length of the string, right? So it's telling you how heavy the string is. So if you have a really heavy string, really thick one, so you have larger mu for that one, larger mass density. Okay, so that's one parameter that the velocity of the wave in the string gonna depends on. The other thing it depends on is the tension. Okay, so unfortunately we used big T for period earlier. So try not to be confused, because in this case T is tension. So tension is how much force you're making the string, kind of, how tight the string is. So you can, if some of you probably know how to play guitar, right? So the tension is essentially like how you turn the knob at the neck, or at the top of the neck of the guitar, to tighten the string. So if you tighten it more, then you increase the tension, the velocity of the wave will change. Okay, so we can go through, but we are not going to do that. In principle, we can go through like a mathematical process to figure out, okay, what's the velocity of the wave in the string, and try to arrive at this to see what is the term multiplying in front of dy by dt, right? So this you can find in the textbook. We're not going to repeat that here. But in any case, in the end, you're going to see that the velocity of the wave is given by square root of t over mu, okay, which is square root of tension over the linear mass density, right? So this is the velocity of wave in a string. So velocity of different kind of wave will have dependency on different variables. For example, if you're talking about sound, then it's gonna depend on the density of air, density of the medium. If you talk about wave in electromagnetic wave, then it's gonna depend on the electric and magnetic property of the medium, right? So this one is just one particular kind of wave, and it happens to depends on these two variables, which is the property of your system. So one is the mass density, and the other one is tension. Okay, so there's maybe one or two, I don't remember, in the question in your homework. That is just a simple plug into the equation. Like you're given the value for mu, you're given the value for tension, and then you are asked to calculate the velocity of the wave. So that's something that you can see and try to get some practice. But before we do that, let's do a little bit of like dimensional analysis to see that if this expression for velocity makes sense or not. Just to see if the unit works out fine. So let's say T is in Newton, right? So I probably did this earlier one. So the unit, I use the square bracket to indicate that it's a unit. So unit of T is Newton. And what is Newton in SI unit? Well, Newton is SI unit, but it's a compound unit, right? So you can break it down into, a collections of, fundamental units. So it's kilogram mass per second square, right? That's the unit of tension, which is just the force, right? Force has the unit of Newton. And what is the unit for mu? Well, mu is mass per length. So it's going to be kilogram per meter, right? Kilogram per unit length, so kilogram per meter. So square root of T over mu has the unit of square root of the unit of T over the unit of mu. So you plug everything in, right? You have the unit of kilogram mass per second square, that's for tension, divide by mu, which is kilogram per mass, right? And you can see that kilogram cancel out. Mass, which is the denominator in the denominator, right? So it's flipped upward. So then it becomes square root of mass square over second square. So in the end, it's just mass per, not mass per second, sorry, meter per second. Okay, m is meter, which is the unit of velocity v. Okay, so the unit checks out fine. And that should be because that's the correct expression for the velocity in the string. Okay, so if you know tension, if you know mu, then you can calculate the velocity like this. Okay, we're gonna come back and use this again when we talk about standing wave, which I believe is gonna be the topic of next lecture on Wednesday. Okay, so you're gonna see that usually you're gonna know the velocity. Okay, remember one diagram that I talked about last time, not diagram, like the summarize of, I summarized the this equation. Maybe I just write it down again. So V equal to F lambda. Remember this one? Okay. What is V? Well, this v is this v. It's the wave velocity, how fast the wave is moving. And that depends on the property of the system. That depends on the property of the medium, right? And that's exactly what we see here. The property of the medium in this case is a string. What's the property of the string? How heavy it is, how tight it is, okay? So it has nothing to do with the source, right? We have not touched any property of the source because V has nothing to do with the source of the wave. V is the property of the media. And that's what we see here, okay? And then later on, we're gonna find some constraint on possible value of the wavelength, okay? Again, we're gonna come back to this again when we talk about sliding wave. But you're gonna be calculating V, and you're gonna know lambda. And from these two pieces of information, you can calculate the frequency of your wave. Okay, so usually it goes like this. All right. Okay, so that's kind of what we have here. So up until this point, we kind of, even though we use a wave in the string as like a study model, but what we talk about up until now actually applies to any kind of wave. Anything that behave like this is a wave. And you're gonna see that this is also true when we talk about electromagnetic wave, which that's gonna be way at the end of this course, and we might not even get to that. But you're gonna see, well, if not in this course, maybe in other course, that electromagnetic wave, right, also satisfy this form. So instead of y, which is the displacement of the string, we might talk about, electric field or magnetic field, right? So if we talk about E and M wave, electromagnetic wave, then what you have oscillating is the electric field. So in the end, what you're gonna see that the electric field, which is the symbol here, right? E with a vector symbol here, electric field actually also satisfy this equation. So you're gonna have something like this, right? So don't worry too much if you don't know what I'm writing down. But I'm just showing you that the electromagnetic wave satisfy also this wave equation. And C here is the speed of electromagnetic wave, which is what we call speed of light, because light is an electromagnetic wave. Okay, so what we talk about here in terms of wave equation actually applies to any kind of wave that you're gonna see in physics. Okay, so it's very important equation, but again, we are not gonna spend too much time solving it. And instead, we're gonna talk about one particular kind of wave, which is the sound wave at this point. All right, so maybe before we do that, if you have any question, you can let me know. If I say something which is still unclear, you can ask me now. If not, then I'm gonna talk about sound wave. So what is sound wave? Well, sound wave is the vibration of, usually air molecules, because we hear sound in air. But it doesn't have to be in air, it can be in water, it can be in solid. Right? We're gonna talk particularly about sound wave in air. And before I do any calculation, let me switch to a presentation so that you can see. So where is my keynote here? Okay. So hopefully you can see the screen. All right. This is what I showed last time, I believe, which is the movement of each particle for sound wave. And if we are talking about air, then each dot gonna represent one molecules of air, which again we cannot see. So we need some cartoon animation like this. So if we run this again, right? So you can see that first of all, sound wave is longitudinal wave, because again, the red dot is oscillating left and right. The wave is also going left and right. Okay, but now what you can see here is something which you didn't see before when you talk about wave in a string. Okay, so wave in a string looks like this. This is wave in a string. Okay, so the particle oscillate up and down, and the wave going from left to right. Okay, so it's all fine. It's pretty clear. The reason why we start with wave in a string, because like everything is probably the as clear as you can ask for in terms of how wave looks like. If we talk about sound wave, then it's a little bit more complicated because the picture or the animation is kind of, a little bit hard to follow. But you can also see how the particle move, which is just oscillating left and right. So you can describe the wave using the same thing that we used earlier, which is the displacement of any particle inside this wave, which is any air molecule. Right. So we can use the y variable again to describe the horizontal, right? In this case, horizontal displacement, not vertical displacement like the wave in the string, because in this case, the oscillation of the particle happens horizontally, right? So even if you use the variable y, okay, as a function of x and t again, but now y is talking about displacement in the horizontal direction from the normal location, the equilibrium location. Okay, so that's one thing that you can do. The other thing you can see is that instead of looking at the displacement of the particle, you can look at what we call the compression and decompression, or sometimes called the rarefaction here. So you can see that maybe you can see like a group of three labels that say compression, rarefaction, moving along with the wave. Okay. So what is compression? Well, compression is the kind of like the band of air molecules bunching together. And rarefaction or decompression is where the molecules kind of like going away from each other, right? So sometimes you're gonna hear the word sound wave as the compression wave, because the wave which is traveling can be thought of the compression, the band of compression which is traveling also to the right, like this. Now, you can use the displacement of the particle, or you can use the compression of the air to describe wave. They are the same thing, but they are what we call like a little bit phase shift. So in order to show that, I'm gonna go to the next animation, which is strictly speaking not really what we are talking about right now, because this is what we call standing wave. This is not traveling wave. Okay, standing wave is the wave where it's not going left or right. It's just it's, the name suggests it's standing there. It's the result of having two waves interfere with each other. Okay, and well, let me just run it. Right. So it looks a little bit different because the wave is not really going left or right, right? It's just there. It's just standing there. But what I want to show actually is the relation between the black graph, which is the particle displacement graph, and the red one, which is the pressure or the compression of the air molecules, right? So on the very top animation, you're gonna see there are two there are actually three red dots if you look carefully. The one way all the way to the right, and then the one to the left, which is kind of like near the center. That one is not moving. Okay, so if you look at the one which is not moving, the displacement is always zero. Okay, because it's not moving. So that's why at that location, the graph for the displacement, which is the black one, is always crossing zero for that particular air molecule, right? So this displacement is always zero. But on the other hand, if you look at the pressure, right, the pressure is actually going up and down at that particular point. So like here, you have the compression because all the friends around it, the molecular friends of, of this molecule is gonna concentrate in that one instant of time. And then sometime later it's gonna go away from each other, so it becomes less dense, so less pressure. Okay, so you can see the phase difference between these two waves, the displacement wave, the black one, and the pressure wave or the compression wave, which is the red one. Okay. Okay, so I realized that the connection was dropped a little bit again. So is it okay now? Can you let me know a little bit if you can hear me now? Hello, hello. Can can anyone hear me? Okay. So, well, hopefully it's better now because I switched to a different network. Um, all right. So I'm just repeating what I said earlier. So if you look at the displacement, right, where the displacement is zero, that's when you have the maximum pressure or compression. Right? Where you have the maximum displacement, right, the peak of the black graph, that's gonna be the zero of the compression graph. Okay, so this is what I talk about when I talk about this phase shift between the pressure graph and the displacement graph. Okay. So all of this is just to show you that you can use either the displacement of the particle as your wave function as something that you use in the wave, writing down the wave function, or you can use the pressure. Okay, it's the same thing. It describes the same wave, right? But anyone is fine. Okay. Um, I think that's pretty much what I want to show for this particular slide. So I'm gonna switch back to my tablet now. And I have to do this. Okay, now I'm back here. All right, so you know what it looks like in terms of the sound wave. Okay, so let's maybe write down a little bit more mathematically on sound wave. So I'm gonna go to the next page. Actually, not that one. Okay. So sound wave. So we can describe sound wave as what we call the wave of compression and decompression, or what some textbook call is rarefaction. Okay, so it's It's just another name for decompression. Where for compression or decompression, that travels through what we call elastic medium. And what does it mean by elastic medium? It's the medium that you can, you can stretch it a little bit. It's kind of like bouncy kind of thing. It's not like completely solid, which nothing in the world is completely solid. So actually, elastic medium is just any medium that you can think of, right? But it should have some elastic property because if you compress it, then it should bounce back. And air is like that. Okay, even though you feel like okay, there's nothing here, but air is actually called elastic medium because if you push the air, then that kind of compression also can travel through air, so it can have sound wave in air. Okay, and again we can describe this as either the displacement wave where the function looks the same as what we had before, so y equal to a, let's say sine kx minus omega t, right? So y now is the displacement of air molecules from their equilibrium positions. Okay, so it's oscillating left and right, where the wave is also going, horizontally left and right. So it's a longitudinal wave. So that means the displacement is also left and right. Okay, it's a little bit hard to picture, but um, that's what we have here. Or you can use what we call the compression wave or pressure wave. And we can write in terms of p x of t, okay? And that's going to be a cosine kx minus omega t like this, okay? So I write cosine here because if we choose the sine to be the displacement wave, then pressure has to be cosine, right? So it has to be kind of, 90 degrees phase shift like this, okay? So this is cosine because this is sine. But I'm just emphasizing the fact that it's the same wave, but it's a little bit different. You're describing the same thing using two different parameters. Okay, but here, this one is the pressure above the regular pressure level of any point in air. Okay. So what do I mean? Well, if you don't have any sound wave in air, the pressure of air at every point will be the same pretty much everywhere, and that's probably not zero, right? Because we know that the pressure can really be zero unless you have zero temperature or something like that. So when you have sound wave, then the pressure at some point will rise above the normal number, and some will go below, right? And this kind of pressure wave is the one that propagates throughout the medium, okay? And essentially that's kind of like what we call sound wave. We are not gonna, repeat everything in terms of, this wave equation, d by dx, d by dt of all of these because it's gonna look exactly the same thing as the previous page. Okay, so we're gonna study more about like how we describe sound wave, how we talk about the sound wave velocity, okay, which is something that more specific for sound wave in this case. Okay, so I'm gonna talk about that after we have this short break here. So I'm gonna set the timer, and then after 10 minutes, then let's come back and talk about that.